All right. So, going to the warm-up. What do we know about this problem?
12 letters.
Okay, we have 12 letters. Okay, what else?
You have a jar.
We have a jar.
Wait, there's letters.
Yeah.
After you select one piece of paper, you put it back in, and then you select again.
So how many pieces of paper are in here every time I select a piece of paper? 12. So, and we have the letters that are on the pieces of paper. We have A through L are the letters. So, question 1 asks me the probability of selecting letter A. So what's the probability of selecting letter A, Logan?
So the probability of selecting answer A is 1 to 12.
Thank you. Okay. Oh, that's frozen. So selecting letter A is 1/12. Kidding me? I don't edit. So we have 1/12. All right. What else? So what is the probability of selecting another A? Jessica. And the reason why it stays 1/12 is because I put the piece of back. Exactly. So here. So it is 1/144. So how do I get this probability? Axel, how do I get this probability?
By multiplying 12 by 12.
Exactly. Probabilities, okay? We know that a probability of one event happening is such, and then the other event happening is such. Whenever I have to figure out the total probability of both events happening, I multiply those events. I do not add. I know, I do not add. Okay? So, Alexis, selecting a vowel. What's the probability of selecting a vowel?
3/12.
Alexis? Okay, so we got 3/12, or that equals 1/4.
You might need a recalculate.
Yeah, I'll recal.
That's such a great sound. Every time you do it, it makes me so happy.
So, here we have 1/12 times 1/12. That's going to equal 1/44. Here, my next one, vowels. There's 3 vowels out of 12 options. That equals 1/4. I can reduce that. So that's the probability of selecting a vowel. What's the probability of selecting a consonant? Cody? 9/12. So basically, because I'm adding a first event to a second event, those events get multiplied by each other. With fractions, I multiply straight across. Easy. So now I get 9/36. Does 9 go into 36?
48.
Yes.
48. 48.
Whoop, 48. Sorry. 9 into 48. Now, is 48 divisible by 3? Yes, because 4 plus 8 is 12. Okay, so I know 9 goes into, 3 goes into 9 3 times. 3 goes into there 16 times. That's fine. So, what does this 3/16 mean? What does that mean?
You'll get that combination.
Chance of getting a vowel and then a consonant.
So, explain to me what those numbers represent. Corwin, recalibrate. Yep.
We got the recalibration on recording.
Yes, we do. It's not the first one. Probably won't be the last. So what does that 3/16 mean? Yes.
What's your chance of picking a vowel first, then a consonant?
Okay, let's go further. What do those numbers mean?
The chance instead of 100, it's like the amount
Of
the
one.
split up. I don't know.
Okay, no, you're thinking, yeah. Say what?
Isn't it like the one? Like
The
out
chance
of
out of
one?
Grace?
Is it that the 3 is picking a vowel and a consonant, and then the 16 is
Picking
Is how many times you try. So if I try 16 times, 3 out of those 16, I'm going to get a vowel and a consonant. Does that make sense?
Wait.
That's what these numbers mean.
So we're counting one trial as like picking twice.
Yep. Mm-hmm.
Which one do they use more often, theoretical or experimental?
We'll talk about that in a little bit. But I want you to understand what these mean. So initially, we had a 9 over 48. That would mean if I did this 48 times, 9 of them, I would have a vowel and a consonant. Okay?
What?
Number 3, selecting a consonant and then another consonant. Well, that's going to be 9 over 12 times 9 over 12. There are 9 consonants. There are 12 options. So that would be a probability of 81 over 144. So what does that 81 over 144 mean? Trinity, what does this number mean?
Means how many times you will actually get constant and the 144 means how many tries.
Yes. So if I did this 144 times, 81 of them, I would get that combination. Theoretically. This is all theoretical probability. It's not experimental probability. And then number 4, what'd you get for an answer there, Jess?
I got 9, so 9 twelves times 1 12.
Okay. So,
On 3, I got
key important thing to understand. When using probability of events, if I have multiple events, how do I find the overall probability?
Okay. So if you have the chance of getting multiple events, then you take the 2 chances of the events happening together with the amount of chances that are possible, and then you multiply that to get your theoretical probability.
I take my probability of the first event, second event, third event, and I multiply those probabilities together. That will tell me the overall probability of that event happening. Does that make sense, Cody? Okay. Go ahead, put your warm-up away. Tomorrow, you guys have problem number 2 on page 59. You might have some opportunity today to work on that as you finish up your lesson. So, just as an extension, I wanted to go over this since we don't have any homework to check. A jar contains 12 pieces of paper. It's the same exact problem. And I randomly select these pieces of paper. So this is what I want you to talk to your partner about. Explain how your probability changes if you do not put the piece of paper back in the jar. Go ahead and talk to your partner. So Axel, we had, what was our probability of choosing a vowel in the last problem? Or in this problem? You can look up here. How many vowels do we have? A, E, I, O, U. So we have A, there's one vowel. E's one vowel. I's one vowel. So we have a probability of 3 12. So what would be the probability if I'm not putting back, if I choose, what would be the probability of now choosing another vowel?
It's higher.
How does that change my probability? Grace?
Grab a vowel, then you'll have a
2 out of 11. So the 2 means I already chose one vowel, now I only have 2 left. And why does it go down to 11? Because there's one less letter that I'm choosing from. Does that make sense? So the game is very different if you're not putting back the paper. It changes. Okay, your probability absolutely changes. Questions about that? Okay, I want you to talk to your partner then. What would be the probability of choosing a consonant and a consonant? Go. Yeah, this way. A consonant and consonant.
Do you choose the consonant on the first?
Yeah, I mean, that's what we're saying. Yeah.
Okay. So 9 12 times 8 11.
And what'd you get, Eric, for an answer?
70 seconds.
133?
72, 11, 132.
32, not 33. 32. So this is our probability now of choosing a constant compared to the probability before, which is that. So if I don't put papers back, does my probability go up or does it go down?
For what? For choosing a consonant?
Constant.
It stays the same. Yeah.
How do I figure this out? Yeah.
I think there's a way you can take both fractions. I think this is correct. And then you
It's way easier.
And
Way easier.
You just convert them both into percent.
Because I can't tell. I can't tell which one is bigger than the other. Which one's larger. So, Eric, what'd you get for 81 over 44? Did you get this fraction yet or no?
56%.
That's 56?
0.25.
All right, so we'll just do 56. So what's this percent? 54. My probability goes down.
oh, because you picked a consonant on the first round.
Okay?
But if you picked a vowel.
Yeah, rechargeable. All right, so you can go ahead. And we are going to look at this right now, and then I'm going to let you guys get going on your maths. So, and I'm going to start half the class that are done. So Calvin, this is, and you'll get this tomorrow in the printout. Today your work is going to be Article 14, 3.1. You're going to label it engagement, 3.1 engagement. We're going to be looking at a spinner, and you can see over here, whoops, God, I forgot to erase some of my work. We have a spinner, okay, that we'll be using. So here Calvin and his dad are in a discussion, okay. They're negotiating about his bedtime. He's on break, okay, and his dad believes he should go to bed at 9 because he has these activities the next day, every day. And his dad's like, no, I want you to go to bed at 9 because that's a good bedtime and you'll be rested. Calvin's like, Dad, it's spring break. I want to stay up till 11. So his dad and Calvin come to an agreement to say, hey, let's do a spinner, like in Chutes and Ladders. We hit something, you spin, and whatever it lands on, that's what you have to do for that day. So Calvin comes up with these spinners. Okay? And Paige just said they're all the same. So it doesn't matter, Paige, which spinner he chooses?
Yes, it does. Stuff onto a wall, like, so it's flat like this.
But it wouldn't be that way, right? That would be. I'd want that one then, right? Because.
He's always getting 9 o'clock probably because his dad gets to decide if he has enough freedom.
So we know that these are all the same. Why are they the same, Fabian? They all have a probability of 50%. This is broken into 4 pieces, but we know that these 2 pieces make half of that spinner.
I feel like the experimental probability would say that spinner 3 is not the best choice.
Although experimentally they're all equal.
Theoretically, they're all equal, right? They just are. So today you're going to use a spinner. Your spinner looks like this. On this spinner, basically you have this. You have a portion that's 11, 9, 9, and 9. Talk to your partners about this. Is this fair? Is it equal? Where'd the 10 o'clock come from? Go, talk to your partner.
Oh wait, that's compromise.
Ah.
Not to the spinner and just do 10 anyways.
Because his dad believes 9 is better. Calvin believes 11 is better. Calvin probably...
Why don't you just do 10?
Well, you think Calvin probably feels that like 10's a win for him, so he'll compromise. His dad feels that 10's a win for him too. It's better than 11, but Calvin still wants to stay up to 11 instead of 10.
Okay, so technically
He is. So, Riley mentioned the 10 o'clock obviously is a compromise that the two of them came up with. Is this a fair spinner?
No. Yeah, because.
Why? Yeah. 10 does have the least. It's definitely not 1/3, 1/3, 1/3, is it? They all do not have a 1/3 probability. What's the probability of getting a 9?
3 out of 8.
3 out of 8.
What's the probability of getting 11?
3 out of 8.
So probability of getting 11? 3 out of 8. Because I have to take my smallest piece and break the rest of my spinner into the smallest increment, which is here, which is actually a 45-degree increment. So if I do that, I have 3 at 11 o'clock too. So you have 3/8 of a chance at 9, 3/8 of the chance at 11.
What's the degree? What's that for?
And, well, that just, because what is this all broken into? 360. Okay, and it just shows you that that's 45, 45, 45, 45, 45, and this is 135. And then the 10 is 2 out of 8, which is 1/4. So, if you're Calvin, would you go with this?
Yeah. Yes. Because. Yes.
Yeah.
No. Because he's still going to die.
Say, now, wait, Chase, explain.
Because 10 is better than 9, so he wins 5 out of 8 times other than 30.
Okay. So we know if I ask for instead of what's the overall probability of two events, if I want to know a probability, what are the chances of those happening, I take those and I add them. Okay, so he has a 5/8, right? He has basically everything on this side of the spinner, so he would hang his on the wall, Axel, with that. That would not be fair. His dad's way too smart for that. So, we know that he has a 5/8 chance of winning. Calvin's dad probably doesn't want him staying to 10, but it's a compromise, right? He's like, okay, that's better than 11. So he also has a 5/8 kind of chance of winning as well. Why would Calvin design this way? What's his thinking here?
Same as my thinking.
Yeah.
His thinking is that it's easier for the spinning thingy, the arrow, to land in a larger space that's all combined than in smaller parts where he could.
So we took a vote. We took a vote last class. And it was interesting because kids voted, like, they said basically, like, oh yeah, that's how I design my spinner because 11 o'clock is going to come up more. So, hold on. And I want to show you. So we took, everyone did the experiment. Okay? Here are our results. Check it out. 37.5% of the time. And that is literally the theoretical probability of getting a 9. And the experimental probability matched it to a T. Wow. The 11 o'clock, even though it's bigger in one space, it's almost exactly the same.
It's bigger.
It was 38.1%.
It's a little bit bigger.
Well, you could manipulate the amount of force you're putting into the spinner so it slows down at the 11. If it's the bigger area, it's a lot easier.
And then,
So light.
so unless you doctor the spinner, the theoretical probability is going to come out true. Whether or not it looks like, yes, this is what I like better than spacing them out, it shouldn't really matter.
Unless you like give it
you, you guys always have but what if you hang it from a wall? You guys have the funniest thing.
What if you were just at the whole spinner 11? And who says he has to go to sleep at night?
So,
I know, just like sleep. Yeah, he can lay down.
Here you go. I guess so. We are going to, Logan, thank you. So, we're going to do the same. We're going to see how we come out. Please don't hang it from a wall. Put a little piece of paper on the 11. Don't do anything. Just for fun, spin it. One of these isn't great, so I'll make sure that we don't have enough. But I want you to spin it 20 times. So how many trials are we going to do? 20 trials. And then we're going to once you do your 20 trials, you're going to go to page 51. And A1 we've pretty much already done. We've done. So you're going to go from A2 on, and then it will take you maybe 10 minutes tops. Hold on. No, you're going to create your own little tally chart. Because that's a lot of work, Sarah.
Yeah, it's 3-1. I have to put my pencil on the paper.
Yes, you do. So, and then we're going to do that. Okay? So this is what you're doing. The kids that are taking the tests. Okay? You're doing this right now. You're going to stay right in here. The rest of us are working independently or with a partner so quietly I cannot hear you. Okay? You're going to spin it. How many times do you spin it, Logan? 20 times. You're going to tally it. And then you're going to go here, answer these questions, and then we're going to do that at the end. Okay. Uh-huh. You guys work together quietly, okay? You two come back.